Okay, for today we are going to talk about the n space. Sometimes referred to as a Euclidean n space. So what do we mean by that? Well, we had studied the one-dimensional space, that's just a real number line you knew from elementary school. Then you took college algebra and you learned about the two-dimensional space. Then perhaps you took calculus 2 or 3, and then you learned about the situation in the three-dimensional space. Well, after that we cannot draw it, but we can have n-dimensional space. They are referred to as a Euclidean because of the way we measure distances and we think about these spaces. Now, so what we are going to talk about could be like a 4 space or 5 space and so on. The general case of this is referred to as a n space. Now, it need not be something like science fiction or advanced physics or anything like that. It's not. We're not talking most of the time about anything all that advanced. We are just looking at a large number of variables. For example, if there are, say, 36 students in this class and I look at their grades, I'll be looking at the 36-dimensional space. Not that there is anything physical with 36 dimensions to it, but since there is 36 numbers, each of them could do their own things, I could think about such a space. Okay. So here you have a point, and that point is represented by a number, so that is just your x, or let's say a. Here you have a point in this space. It has dimensions or coordinates a and b, and you talk about a point being same as a pair of ordered numbers. Number 1, number 2, or how much you go to the right or how much you go up. Here, a point is represented by 3 numbers, say A, B, C. Or you can think about the vector that is represented by these 3 numbers. In general, if you have a 4-dimensional space, so it's going to take 4 numbers to represent that. So after an exam, you might have 36 numbers, so you have 36 numbers to deal with. If you do advanced engineering, you could have 100 million numbers. It's a 100 million dimensional space, but perhaps those are all the points on some scattered on the wings of an airplane. Each of them has its own locations and characteristics. You're talking about them. In general, if you want to talk about something n-dimensional space, this alphabet's not going to be all that effective, so you index them x1, x2, x3, and then somewhere you have to resort this ellipsis notation, and then xn would be the last item that you have here. Well, how do you handle these things? What kind of things can you do with them? Like you want to introduce some sort of a game. Well, the games that you have with these kind of vectors, exactly same thing that you had before. So just for the sake of practice, let's take a few vectors in, say, 4 dimensions and learn how to add, subtract, multiply, measure the length, measure angles, and all such things. And again, none of our formulas are going to be new. So let's pick 2 vectors. I take a vector A, say 1, 2, 3, 4, and vector B, say 5, 1, 0, 6. So if I talk about A plus B, now we don't have the luxury of being able to show them because there's no easy way of visualizing a 4-dimensional space, so we just resort to algebra. A plus B, just add up the corresponding elements as might be suspected. Negative of a certain vector is just multiplying all of its entries by -1. Subtraction of 2 vectors is simply addition of 1 to the negative of the other one. So again, it just comes naturally. You're subtracting these 1 minus 5, 2 minus 1, 3 minus 0, 4 minus 6, and so on. Then we had the idea of a scalar multiplication. Said when it comes to multiplication, there are all sorts of multiplications. The easiest one is take an ordinary number, which is now called scalar. So scalar is just another word for an ordinary number. 2, 3, pi, e, all of these guys is just one single item. We call it scalar. So if I was talking about 2a, I'm not really doing anything fantastic. I'm doubling every entry of this vector. So if it was pi times a, I'm just taking pi and multiplying by entries of that vector. Other than scalar multiplication, we had things that were a bit more advanced, and principle among them was the dot product. Dot product, here we have the dot product as well, and again it comes with two formulas. One of them is component based, so let's write down one. We have two styles. One is component based multiplication, and the other one is kind of length angle formula. Component based, it means you so a times b, that is 1, 2, 3, 4, dotted with 5, 1, 0, 6, and that means 1 times 5 plus 2 times 1 plus 3 times 0 plus 4 times 6. And then don't forget you're adding these things. The common mistake is to just leave some loose numbers around. The result of this is supposed to be, it produces a number or a scalar. Ordinary number comes out of it, not a collection of numbers, not a vector, but just a single number that is like 5 plus 2 plus 0 plus 24. So that is presumably, say, 31. We also had the length angle formula for the dot product. What was that? Length of A, and I mentioned I write it like absolute value notation, but the book insists on using double vertical bars, just that becomes too crowded here. Now length of A times length of B times cosine of theta. What do we understand by length of a vector? Exact same notation that we had before. So if you want to calculate the length of A, we did it in 3 dimension. In 4 dimension, exactly same thing. You square all the components and add them up. Application of Pythagorean to high dimension. So you have 16 and 9, 25, and another 5. Looks like 30. How about B? So that was our B. B is going to be 5 squared, 1 squared, 0 squared, plus 6 squared. Remember, if you had any negative component, when you square them, it becomes a positive quantity. So no negatives staying here. 26 and 36, I guess that is going to be 62. So what does theta angle theta refers to? Theta is angle between A and B. Now since we couldn't see A and B, they're sitting in a 4-dimensional space, showing theta to you as a physical item is not going to be easy either. But you can imagine always two vectors define a plane, regardless of what dimensionality you might have. Once you have two vectors, always define a plane, and in that plane there is an angle between them. Now you might not be able to see this one or that one, but you can always figure out what is the angle between the two. So in this case, we can use the fact that this product, okay, this definition and this definition referring to the same thing, and we can use this as a double-edged sword to figure out the angle. So for example, if I want to figure out cosine of theta here, what would it be? So cosine of theta is A dot B, which I figured out here, divided by length of A times length of B. Okay, so you always have this formula. You can turn this formula around. You can say cosine of theta is dot product of the two vectors over product of their length. So you can figure this out on your calculators, see what that one is, and then use the inverse cosine to figure out what theta is going to be. So that's going to be arc cosine of you make sure when you want to write down, you put the units next to it. Your calculator shows, is it dealing with radians or is it dealing with degrees? Occasionally you might leave your calculator in the grad mode. Nobody cares about grad all that much. So you either have radians or you have degrees. One of these two, make it clear which one it is, and then you produce a number. So that is the angle between my vectors. All the rest of the formulas are still the same. That is, if I were to ask you what's the projection of A over B, yes, very good. So this doesn't have anything to do with how many dimensions you happen to be living in. Just carry this out as usual. So if I want to do this, I say A dot B. Here I did the A dot B, so I might just borrow, that is 31. B dot B, can you tell me what's B dot B quickly? By peculiar coincidence, that became the exact double of the other one. Then who's B? B is whatever you got here, so that is 5106, happens to be a half, so it turns out to be 5 halves, 1 half, 0, and 3. So the shadow of A over B turns out to be half as long as B, and that's it. Any of the questions in this section are just done exactly same as before. You just are dealing with more components. Okay, I suppose these are pretty much all the same. Here perhaps one question with slightly different terminology. It says find R. This is problem 20 from 3-2. Find R such that combining all the stuff that you have learned here, let me see if you can give an interpretation for what this problem is looking for and how to go about finding it, finding the answer. So find this R such that the absolute value of that number times this vector is 1. We are looking for what? We're looking 2, 3, and so on. If you have a vector, it just let's go back to example we had here. Let's do easy vector. Suppose if you have a vector A, what did we say the length of this thing is? We did it over there, was 30, was that right? That is square root of that sum of those squared, so whatever that is, 1 squared plus 2 squared plus 3 squared plus 4 squared, and we got 30. Now if I double all of these things and I ask you find the length of that, or triple it, or multiply it by 5, say I multiply it by 5, what do you think is going to be the answer? 5, yeah. Not a big surprise. If you take a vector, multiply it by some number, like you are stretching it 5 times, then its length is going to be 5 times. How does that come out in algebra? Well, if you take 5 and multiply by these, square them and add them up, then that factor of 5 squared can come out of this radical and just moves outside. Okay? Now, here you have two options. You can take the r, multiply by all of these. Let me do it 2 different ways. You'll see all the same. One of them is going to be a lot cleaner than the other one. If you have an unknown quantity r, you are multiplying by this, your vector by now is r, 0, minus 3r, minus r, 4r, and 1. Is that right? Oh, excuse me, and r. So suppose you want to find the length of that. How do you find the length? You have to square everything and add them up. Square of this one is just r squared. Square of 0, well, that's just 0. What is the square of minus 3r squared? It's 9r squared. And this one, r squared. 16r squared. Another r squared. How can you clean up this stuff here? How many? Yeah, so we have r squared. 1, 9, 1, 16 plus another 1. What's my total? 25 and 3 is 28. Is that right? What happens to the? You can pull it out. Well, square root of r squared is a little bit tricky here. What's the square root of r squared? Well, the absolute value of r. What do you want from this whole thing? You want to determine r such that this length becomes 1. So you want this to be 1. So r becomes 1 over square root of 28. Well, 1 over square root of 28, you can clean it up a little bit. 2 square root of 7. So what are the possible values of r? Yeah. Positive, negative of we could do this thing from the beginning. We could say take the r out, find the length of this vector, which we just did. Okay, once you see this problem a couple of times, you can go about it a lot faster. You say, okay, if I have a multiple of r inside of this length, I can pull it out. It's going to still stay inside the absolute value. Like if it was positive or negative, it comes out as a positive quantity. The length of this is 28 square root. Right hand side of my equation is just 1. So what does that tell me? Same stuff as before. 1 over square root of 28. R would be either of these two possibilities. Okay, so that's perhaps the only case where the language is a little bit different. Now, some of these problems, these vectors are written horizontally. Some of them, the vectors are written vertically. It does not make any difference for us. We don't have any way of distinguishing between the two. That is, the same problem could have been posed like this. It just would have looked very strange to write it and would have taken a lot of space in the book. But it's exactly the same problem. So r times this vector in absolute value is supposed to be 1. Question would be, what is r? The answer to that problem would be same as this. There's no difference so far. if you're writing it horizontally or vertically or slanted or whatever, it's just a collection of ordered numbers. We don't have anything else. Okay, so this was section 3.2. I forgot to mention this is section 3.2, and we want to go to next section that is a little bit more fundamental, more basic, sometimes even more interesting. So 3.3 is so-called general vector spaces. The intention in this section is to dig in deeper and try to get at the bottom of what is it that's really responsible for behavior of these vectors. What is it that they have in common? Trying to create an abstract picture and not to be too much tied down to specific examples. Like so far, vectors for us were either collection of numbers or arrows in space. Those are things that we are very familiar with. Sometimes we come across things that are not as familiar. Perhaps they look different. Perhaps previously they had different names, and now we want to come back to them and say, well, actually those guys also are essentially some kind of vectors. So we want to find the general definition of what is it that is really makes a vector space. Vector space is made out of two sets. Okay, so there's one set, let's call it V. This is the set of your vectors. And then there is another set, well, we might call it, say, F or something. These are your scalars. So these vectors could have been just any of these vectors we have been talking about, like two-dimensional vectors or three-dimensional vectors. Any one of them would be a good example. Like set of all triple ordered numbers, or set of all vectors with 5 components and such. Scalars, these are just going to be our ordinary numbers. If you take the next linear algebra class, they are going to generalize this one as well, but we are not going to have any use for that right now. Our scalars are just ordinary numbers. At most, we are going to go to complex numbers later on in the semester, but we are not going to talk about anything beyond that, even though there are things beyond that. Okay. These vectors that we have, we are going to pick some representative members of this. We might call these guys like little v and u and w and such. The scalars that we have, we might call them by some different names, say x, y, z's, or r, s, t's, and such, typically used to indicate your scalars. Now, to make a vector space, we require certain things to happen. One of them is that we have a notion of addition, and we have a notion of scalar multiplication. What we mean is that if I take any two vectors and add them, I get an answer that is still one of the member of this clan of vectors I'm considering. So in a certain sense, our clan or tribe is kind of closed. If you take any pair of elements from here and operate on them by this operation, whatever comes out of it has to stay inside of that tribe. So if I have an arbitrary member of my vector space and another member of that space, is the result of adding the two of them is in my original vector space. So it is not like we add two things and all of a sudden you create a creature that is something totally different. We are not playing Frankensteins in a lab or something. Whatever we do, whatever comes out of the experiment in the lab was already on one of the shelves on the lab. We are not creating anything new. We are staying inside. So this is one of the concepts of the closure that we have. Another one is a scalar multiplication, meaning if I take any of these vectors, multiply by any of these numbers, whatever comes out is still inside of that big set. So if I have a scalar like 2, 3, 5 or whatever, multiply by any one of these vectors I got, the result is in the original vector space that we had. This is referred to as closure with respect to, this is with respect to addition, and this one is called with respect to scalar multiplication or just multiplication. This is the biggest concept that we have here, this concept of closure. Everything else is going to be repetition of whatever we have seen before. So let's emphasize the concept of a closure and talk about it some more. To talk about that, I'm going to take some other sets. Let me consider the following set. Set of odd numbers. What do you mean odd numbers? 1, 3, 5, 7. Together with the negative of these guys, if you wish. Let's practice this concept with respect to this simple set. So is O closed under addition? What do you think? If you add two odd numbers, the question is, if I pick two of these things and add them, would the result still stay inside of the original set I had? Obviously, the answer is no. Is O closed under multiplication with its own members? What do you say? If I multiply two odd numbers, what kind of a number do I get? So I'm talking about closure with respect to multiplication with its own members. And there the answer is obviously yes. Let's pick another set. Let's call this set P2. Set of all polynomials in some variable, let's call its variable, say x, up to order 2. What do you mean? Well, an example of this, like if I take 3x plus 5, or I take x squared, say minus 5x squared plus 7x plus 11, this is a polynomial of order 2, which is a member of P2. This one happens not to have any x squared in it. Or I could have just a number in it, no x squares, no x, just a number. So if I take some multiple of x squared and some multiple of x and some plain number by itself, where a, b, c are just my numbers. The collection of all such things is going to be referred to as P2. Set of all polynomials in a variable name is x. Up to order 2 means constants and linears are okay too. But what is it that is not in it? Like I don't have x3 plus say 5x plus this is not going to be in it because degree is 3. So polynomials of order 2 or of degree 2, all of them is inside of this P2. Question: is P2 closed under addition? Which means if you take two of such polynomials and if you add them, do you get something surprisingly new? No, it's still inside of that set. So P2 is closed under plain addition. Again, if I take two such things and add them, I'm going to get one more of these kind of guys. I'm not going to get like an x cubed coming out or x to the power of 5 coming out. My power never increases. It's possible that you add them and the power decreases. Like you might have 3x squared plus 7x plus 11, and the other guy is minus 3x squared plus say 5x plus 2. If you add them, what do you get? Say 12x plus 13. X squares could, so the degree could go down, but can't go up. So P2, set of all polynomials up to order 2. Is it closed under addition? Yes. Is P2 closed under scalar multiplication? Now, we don't mean to multiply two of these guys, but rather take one of them, multiply by some number, like double it, triple it, quadruple it, or something. Would the result still be inside of this set? Yes. So the answer is yes. Sets that have both of these properties are essentially vector spaces. Any set that has a property of being closed under addition, you take two of them, it's like having two vectors. You add them, you just get another one, something like this. If you take any one of them, multiply by anything, it is still inside of your set. That is, as you stretch it, you are not leaving a space. As you add them, you are not leaving a space. Anything that has that property is essentially a vector space. Vector spaces have the same properties we mentioned before. Let me just go ahead and list all of these things just for the sake of completeness and just to make sure that we are not skipping. So if you have one vector and then you have another one, you can add them. And we said by closure property, the result has to be still inside of that space. Well, what do you expect out of this addition? Whatever you learned from way back when, you still expected that addition is commutative. So we still have that. What else did we have? Well, we had that if you are trying to add three things, sticky question comes up as to what do you do first, and the nice answer is, well, it doesn't matter what you do first. It's the same thing. So addition is associative. What else we have? We have something called the zero element, which has the property if you add it to anything, it does not change it. So existence of zero element or identity element of addition. So we have a concept of a zero vector. So in the text, these are shown in bold notation, so you separate them from or distinguish them from ordinary vectors. And then once you have a zero vector, there is a concept of a negative vector. Each vector comes with a pair, and that is shown as negative of v, such that if you add them, you get that zero vector. So this is a negative element or additive inverse. So whatever set you are playing with, there has to be these two properties in it. Somebody has to be nailed down as playing the role of 0 for you. For any vector you got, there got to be another one which plays the role of negative of that vector. Plus, we have a bunch of distributive laws. Like if you have a number and you multiply it with the sum of two vectors, well, you can do it in another way of multiplying that number with each of these vectors first and then adding them later. So we have this distributive law. Well, there are actually two of them. I could have two numbers added, multiplied by a vector, and as you might suspect, we still have this kind of distribution as well. Once over the vectors, another time over the scalars. We also have an associative property that if you have product of two numbers multiplying by a vector, you can have one of them wait outside until one of them multiplies with that vector and the result's still the same. Moreover, we have to make it clear that whoever plays the role of 1 here, when you multiply it by a vector, it should not make a difference. So these are, excuse me. We still have this distributive property. So we have two distributive laws. We have associative property of multiplication with scalars. We have identity element of multiplication. So whatever set you are trying to sell me as a vector space has to have closure property. Okay, so first you have to identify who are your vectors. Then you identify who are your scalars. Almost every example in this text, your scalars are just ordinary numbers. You have to specify what you mean by addition. You have to specify what you mean by scalar multiplication. You have to show that when you add things, you are still inside of your first set. When you multiply by numbers, you're still inside of your first set. This is called the closure property. This is the main thing that you typically do in any of the problems. It's just that we want to keep in the back of our mind that whatever you are trying to sell as a vector space satisfies these basic requirements that we have for a vector space. Now, best thing to do is to practice a few examples to see what to expect, what kind of language to expect, and okay, let me go toward the bottom so that we get something a little bit past the trivial language games. So this is problem 25. It says, consider the following set. The book calls it M33s. These are these particular kind of matrices, A, B, C, 0, D, E, 0, 0, F. So what is the name of these guys? We call them upper triangular matrices. These, if you want to describe it in words, these are 3 by 3 upper triangular matrices. So I'm introducing you to this set. And now I come and claim, or I ask you to show. What would I be asking you? Show M33 is what? Is a vector space. What do we mean by this? First of all, we expect a way of being able to add these kind of things or multiply them. And those things are no surprise. How do you add two matrices? Just the way we had learned how to add them before. If it meant anything different, we would make it clear. How do you multiply a matrix by a number? The way you have been doing it all along. So typically, this portion of expectations already satisfied in these basic problems. What is expected of you to understand or to show or show it doesn't exist is, do these guys have closure property? What does that mean? If I take two such things and add them, what do I get? If I get two upper triangular matrices and add them, could it be that I get a lower triangular matrix out of it? No. This zero structure is going to survive my operation. Is that right? Like if I take two of these things, like one of them is 1, 2, 3, 4, 5, 6, and the other one, say 5, 7, 11, 9, 18, minus 6. If I add them, do I know ahead of time that these zeros, at least these, will be in the answer? Yes. That's all I care about. I don't care about what is sitting here, so long as the shape of the answer make it to be a member of what I had at the beginning. I got one down. Second thing, if I take one of these matrices and say double it or triple it or multiply it by any number, would it preserve its shape? Meaning, can I guarantee that the answer would still have zeros here? Yes. Like if I take 5 multiplied by one of these, what can I guarantee without multiplication? That these entries are 0. And that's all I care about. I don't care about what is sitting here. The set that I was trying to target had a particular look to it. These elements of it were nailed down to be 0. The rest of it could be anything. And I say, is that set closed under addition and multiplication? Yes. Now, just as a matter of contrast, let's see. If I had given you another set, let's say F33, say A, B, C, so this notation means A, B, C, D, E, F, they are arbitrary numbers. Here, I am assigning the value 1 to these lower triangular entries. Question, is F33 a vector space? No. Obviously not. Why? You add two of these guys, instead of one, you're going to have two. And in our set, we are only targeting the ones who have a 1 here. So it's F33, we are insisting that these guys got to be 1s. Well, if you add two of these things, you are somewhere else. If you take one of these things and multiply by a number, anything other than 1, well, these numbers are going to be different. And your set is not going to be still this set. So the answer is no on both counts. If one of them is missing, then the whole thing falls apart. Now let's go take a look at some other examples. Say 28. Book says call it M22. These are matrices of the following type. So again, we have a collection of stuff. Our stuff are these. They are matrices, but now we can call them a vector if you want. They are members of a vector space. For what reason? We check to see, is it closed under addition? Is it closed under scalar multiplication? Let's understand what is meant here. Let me give an example. Suppose I have 7 and 5 on the diagonal. What should I have off diagonal? What? 12. Suppose I have another one which is like say 2 and 4. What should be off diagonal? 6, 6. Why 6, 6? Because we are insisting that these have to be some of those. Now if I take two of these things and I add them, would the property still stay there? 7 and 2 is 9. 5 and 4, by peculiar coincidence, that's 9. How about 12 and 6? That is same as the number that I get from adding these two. That is 18. This is 18. That is, if I add two of these, I get something where these members are the sum of the other members. Now that just gives a justification to say that M22 is what? Is closed under addition. Now, how do we really show it? I'll say take one of these guys. If it is A and B here, the other ones are nailed down to be A plus B. If the other one has C and D in it, here has to be C plus D and C plus D. If I add them, what do I get on the diagonal? A plus C here, and B plus D here. Now, what's the property of this? That is the sum of the diagonal entries. And that was the property of the original matrix, that whatever diagonal entries I got, the off diagonals are the sum of these two. Well, the same property is preserved by whatever comes out of this addition. So it's closed under addition. Similarly, you show that it is closed under scalar multiplication. Now we have to write this with the language of proof a little bit better than this, but given that we have so much other thing, that is all that is expected from you for now. So make sure that you go through the exercises of this section. You need to do a lot of exercises here. All of them are kind of by inspection. You have to be able to look at it and come up with a verdict, yes or no, and have a clear idea of why yes or no. So you want to do 3, 4. As many of these things as you can do is going to be best for you. Okay, so I'm going to see you on Wednesday. Prepare your question. I'll be answering. Good luck in class.